In this presentation, we're going to learn about the paired t-test. And basically we have two populations, and what we're trying to do is we're pairing them and then we're going to compare them. So let's kind of talk about what this actually means. So imagine you have two populations. So let's say we have population 1 and we have population 2. And inside these populations are things we are going to look at or measure, let's say. And these things are usually connected between the two samples. So we know that there's like some sort of connection between them. For this video's application, we're going to consider two different solar cells. And the first solar cell is a silicon monocrystalline and this is the second population is a silicon solar cell, but it's polycrystalline. And these two different types of solar cells represent sort of the most abundant solar cells that are currently on the market. And so let's say we want to determine whether or not one is better at producing or converting the sun's energy than the other. So let's say we want to see, alright, is the mono better than the polycrystalline? And this is of course if we hold every other variable constant. So it's the same house, it's the same setup, they're put in the same type of array, etc., etc. So what we're going to do is we're going to, in this test, is we're going to measure the amount of electricity generated by each solar panel each day. So we'll have day 1, day 2, day 3, again day 1, day 2, day 3. And what we're going to do is we're going to compare the energy generated for the mono and the poly for each day such that it compares with the corresponding population. So this one essentially pairs with this one essentially pairs with this one, and etc., etc. for however many days we actually conduct this experiment. So to actually go in and figure out what the difference is between, our mono versus poly populations, what we're going to do is we're going to conduct a hypothesis test on the mean difference. So in this case, it's the mean difference. So you'll note that in previous hypothesis tests, we've basically just been looking at whether or not our population is equal to the mean, or it's less than, greater than, or not equal to the mean in some way, shape, or form. But in this type of test, in the paired t-test, we're looking at the difference, so the mean difference between two different populations. So what does that actually look like? So for both a mono and a poly performance being the same, we're going to have a null hypothesis that basically says that the difference is equal to 0. So that's basically saying that the mono and the poly solar cells are performing exactly the same. And then our alternative hypothesis basically says that the difference is not equal to 0. In this case, as you can tell, this is a two-sided test. And again, it's because we are looking at whether or not it's less, or that the possibility that in the alternative hypothesis that it could be less than or equal to 0. So it can either be more than or greater than. And further, it's a two-sided test because we're not guessing a priority, or what we would call in advance, which specific solar panel type, so mono or poly, will perform better than the other. So what we need to do is we need to go in and we need to start defining certain things. So what we're going to do is we're going to denote X sub I as the energy produced by the mono on day I. And similarly, we're going to denote X sub I as the energy produced by the poly on day I. So our difference, which we're going to call di, is essentially just X sub I minus Y sub I. So this is the difference in energy produced on day I. So to actually go in and perform our test, what we need to do is we need to compute d bar, which is the sample mean of our collection of di's. So what we're going to do is basically compute the mean of all of our differences for each day. And then we also have to compute the SD, which is our standard deviation based off of our sample. Of the collection of di's. So the standard deviation also is based off of the difference. So using these two values, we can then go in and compute the test statistic T naught, which again uses the student's t-distribution. And that equation is d bar minus the difference of naught. And in our case, we're going to get rid of this because it's equal to 0, because we're basically saying that there is no difference between them, so it's 0. And that's divided by our SD divided by our sample size n. So again, just wanted to remind you that our T naught uses the student's t-distribution. So basically, we can go to Excel. So in Excel, you'll see that I've gone in and I've collected some data. And essentially, I have 11 days, so our sample size is going to be 11. And I have kilowatt hours, so the energy that we've collected or measured for our monocrystalline for days 1 through 11, and then also for our polycrystalline silicon for days 1 through 11. So the first thing we need to do is we need to compute di, which is essentially our xi. So what I want to do is denote this as xi. So we'll make this a little bigger. And this, our poly, remember we called yi. So we're going to make this a little bigger. And our di here is just the difference between the two. So we're just going to subtract x sub I minus y sub I, and we're going to carry it all the way down. And then what we're going to do is we're going to compute our d bar and then our SD. So our d bar, again, is just the average of all of our di's. And then our SD is just the standard deviation, and in our case it's a sample of all of our di's. Press enter. And so we've calculated d bar and SD. So the last thing we need to do is we need to compute our test statistic, in our case, T naught. So our T naught is equal to d bar minus our delta naught, but again, because we're saying that we're testing the differences between the two such that they're not, such that they are equal, so we're saying that that difference is 0, we're not going to include it. Then we're going to divide it by the standard deviation divided by the square root of our sample size, and we've computed a T naught of 17.34. So the next thing we need to do, essentially to determine whether or not to reject or not reject the null, is to first compute a p-value, and then we could also do it based off of a confidence level, and we're going to do both. So the first one is to compute p, and to compute p using the student's t distribution, we type in t dist, and in our case we want to use absolute value if our t naught value is negative. In this case it isn't, so we're just going to type that in, and our degrees of freedom are n minus 1, so in this case L3 minus 1, and then our tails, in this case it's the 2 tails. We're going to hit enter, and we get a really, really, really low probability. So this is basically telling us that we can reject the null. But let's do it based off of the confidence level as well. So let's say we're going to arbitrarily choose an alpha value of 0.05, which is pretty standard. And then from this we're going to calculate our critical value, which is our t alpha over 2 value at n minus 1. So t alpha over 2 n minus 1. And to do that we use the tinv function, and we put in our probability, which is our alpha value, and then our degrees of freedom. And this tells us that our t alpha over 2 n minus 1 value is between negative 2.23 and positive 2.23, and our t naught value does not fall in that area. So because of that, we're going to reject the null. I hope you have a better understanding of paired t-tests. Thanks.